All right, here's a few more examples for free body diagrams. Let's see. All right, let's start off with a box moving. Well, let's be more explicit. Let's say a box is pulled to the right at a constant speed. Okay, so we'll start off with the box as a dot. And then we'll think about all the forces acting on the box. I can think of force due to gravity. I've got normal force, and there's a pulling force. Let's call it tension. It's pulled with a string, and it's on a surface now. Box pulled to the right. I mean, I guess it doesn't say it's on a surface, but let's put it on a surface. So there's friction. Box pulls to the right on a table, something like that, at a constant speed. So we've got force due to gravity down and normal force up. And they don't give us any numbers, so can't add any labels. But I do know that the box isn't accelerating off the table, so I'm drawing the normal force and the force due to gravity equal and opposite arrows. Then I know it is being pulled to the right at a constant speed, so I'll draw an arrow to the right and label that FT. And since it's at a constant speed, I can think ahead and realize that the net force horizontally must be 0 because there's no acceleration when it's at a constant speed. So I'm going to draw the friction force, the left one, equal and opposite to the tension force. And you can add tick marks here if you want to indicate which ones are equal to each other. This is an object that's moving at a constant speed. Yeah, I'm doing a quick video. Let's do that same box accelerating. Okay, so in this case, we've still got FG down and FN up. Still got force due to tension on the right. But on this diagram, I'm going to do the left, or the friction, just a little shorter. In this case, the horizontal forces are not balanced. There will be a positive net force, or a non-zero net force, and it would have an acceleration. For example, if your tension force is 10 newtons and you find out your friction force, well, watch this. Say, this is cool. You can actually find out a lot more if all you have is the pull force and the mass of the box, let's say, is 1 kilogram. So if the mass of the box is 1 kilogram, I know that 1 kilogram times 10 meter per second squared is 10. So force due to gravity is 10 newtons, which makes the normal force 10 newtons. So I can label that there. And I know that force due to friction is mu multiplied by the normal force. And now I know the normal force is 10. Now they would have had to tell me what two surfaces it is. But let's say the coefficient of friction between the two surfaces is 0.5. Remember, there's no units there. So I would have force due to friction equals 0.5 multiplied by the normal force, which is 10 newtons. So the friction force would be 5 newtons, negative to be exact, because it's going the other way. I guess mathematically, ooh, that's annoying. I'll have to figure that out. So say that is negative 5 newtons. Okay. Let's make the pulling force bigger, like 20. So now this is 20, this is negative 5, and we can sum up the forces in both directions. Sum of the forces in the x direction and sum of the forces in the y direction. In the x direction, we're going to have friction plus tension, and in the y direction, we'll have normal force plus gravity. And so our friction will be minus 5 plus 20, and normal will be 10 plus negative 10. Y will be 0 Newton. net force. And in the x direction, we'll have 15 Newton to the right. There you go. So that's kind of the game. These are the free body diagrams. And this is what you can do with them. Huh? Have a good day, folks.